Welcome to the Organic Chemistry Podcast, Dr. Brian Lloyd's scribblecast of organic chemistry lectures and solutions to homework problems. In this lecture, we are looking at alcohols, ethers, and related compounds. Alcohols and ethers are polar molecules. The polarity of these molecules decreases as the oxygen becomes more and more substituted with alkyl groups. They are derived from the molecule water. Water, or H2O, has a single oxygen with two lone pairs. As we substitute hydrogen for carbon, we change the functional group. The first carbon producing what is called an alcohol. When we replace the second hydrogen with a carbon, we produce the functional group ether. R here is some kind of alkyl group. So R equals, in this case, alkyl. Now, ethers, interestingly enough, can be straight chain, such as this molecule, for example. This is one of the oldest known ether molecules. It dates back in recorded history to the 1500s. As such, when someone just says ether, they're typically referring to this molecule, which we refer to as diethyl ether. Two words. Now, they can be straight chain, such as this, or they can be cyclic molecules. This molecule is given the abbreviation THF. THF comes from the word tetrahydrofuran. This name actually comes from a common molecule. This molecule right here is furan. And furan requires 4 hydrogens to become fully saturated in the pi bond area. There are 2 pi bonds which need an H2 gas each to get rid of them, and that's 4 hydrogens, hence the name tetrahydrofuran. Another cyclic ether is the molecule here, which is called, this is 1,4-dioxane, which is a cyclic ether. So cyclic ethers are as common and useful as solvents as straight chain ethers. A very interesting polyether is referred to as a crown ether. Here is a crown ether that is referred to as 18 crown 6. Crown ethers get their name because when you look at them edge on, the oxygens point up so that the base of the ring forms what looks like a crown. And you see crowns in back. And so what you see are the oxygens at those dotted positions. And effectively, your molecule looks like a crown. Now, crown ethers are very useful for dissolving inorganic salts and organic solvents. You know, we have done substitution reactions. We have used, as a reagent, hydroxide. Hydroxide is often reacted as a sodium salt. But sodium hydroxide is ionic. Methyl bromide is organic. How do you get an ionic compound to dissolve in organic solvents? Well, one way is to attach it to an organic material that will make the ionic species organic soluble. You can design a crown ether so it will actually fit a cation in the middle. such as sodium plus, for example. Sodium plus ions are very large, and the oxygen atom lone pairs can interact with sodium ions, effectively designing the pocket so it just fits. Now, I'm not sure that 18 crown 6 is the right size for a sodium ion, but you can design a crown ether with sufficient number of oxygens and sufficient ring size so the sodium just fits perfectly. The oxygens lone pairs interact with the positive charge. Now the sodium ion, because of the organic groups hanging off the crown ether, can be made to be organic soluble. Hydroxide would closely associate with the sodium, and the crown ether would cause the sodium hydroxide to become organic soluble. And then you have your hydroxide delivered to your organic reagent. So crown ethers are very useful in laboratories. Another cyclic ether is given its own name because all of these ethers essentially are non-reactive and make good solvents. But this ether, which has a three-membered ring, is very reactive. So if the ether is part of a three-membered ring, it's called a functional group, not an ether. It's referred to as an epoxide. And the reason it's given its own functional group name is in terms of reactivity, it's very different. Epoxides are not good useful solvents because they tend to be very reactive. This is caused by the ring strain in the molecule and the tendency for the ring to pop open. So epoxides are very reactive. This molecule is referred to as an epoxide functional group. Its common name is ethylene oxide. 2 words. Its IUPAC name, we're going to learn, is Oxirane, which probably comes from oxygen in a ring, Oxirane. Notice how oxy is spelled. Do not use a Y here. Okay, let's discuss the physical properties of our molecules that we're looking at. Let's begin with alcohols. Well, as is obvious, alcohols have the OH group and hence have hydrogen bonding. Because of the hydrogen bonding, alcohols tend to be higher boiling in terms of physical properties than corresponding similar molecular weight organic halides. Ethers, on the other hand, lack the OH group. They lack hydrogen bonding. Now remember, hydrogen bonding is not a real bond. It's kind of a misnomer. It is an intermolecular force. It's much weaker than a bond. But because of the lack of hydrogen bonding, ethers are much lower boiling. Ethers can hydrogen bond to water because of the lone pairs. That is, water, which has hydrogen bonding, can hydrogen bond from its hydrogen to the lone pairs on the ether. Because of this, we're going to find out that ethers are capable of dissolving in water. So although ethers themselves can't hydrogen bond and it doesn't help the boiling point, for solvation purposes, other molecules can hydrogen bond to the ether's lone pair oxygens. Now, low molecular weight alcohols are miscible with water, as well as low molecular weight ethers. By the time you get to 4 carbons, however, water solubility decreases. So while ethanol and propanol are water soluble, by the time you get to 4 carbons, the solubility in water has been reduced to 8 grams per 100 mils. Solubility of this alcohol in water is only 8 grams per 100 mils. What's interesting is because, and this really exemplifies the fact that water can hydrogen bond to an ether, diethyl ether, which also has 4 carbons, effectively has the same solubility. And one could argue and say, well, hold on, butanol, 1-butanol, has OH bonding. Ether doesn't. How can ether be water soluble? But the fact is, ether may not be able to hydrogen bond to water, but water can hydrogen bond to the lone pairs on the ether. And so likewise, diethyl ether is approximately 8 grams per 100 mils solubility. However, with regards to boiling points, the boiling points are hugely different. Whereas butanol will boil in pure form at around 117 degrees Celsius. I'm not sure about that value. I know it's pretty close to that, somewhere between 111 and 117. Diethyl ether has a boiling point of somewhere around 34 or 35 degrees Celsius. Now the difference here is really bringing out the difference in intermolecular interaction. Butanol molecules can hydrogen bond to each other. Diethyl ether molecules cannot. Another interesting point occurs when you consider 4-carbon alkane molecules of different size. What do you mean? Well, 1-butanol has a long straight chain of carbons. If you look at tert-butyl alcohol also has 4 carbons. But it's nearly has infinite solubility in water. If it's the number of carbons, why would 2 4-carbon molecules vary in this way? Well, the long organic chain, straight chain, is mobile. It flip-flops all over the place. And effectively, this long chain can sweep water molecules away. That would solvate the OH group, reducing the solubility. But tert-butyl alcohol is almost spherical with its methyls here, 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 and its OH. And because of its spherical nature, water molecules can make closer approaches to the OH group, and more effective hydrogen bonding can occur. When you have this straight chain, this chain can swing around, can flip-flop if you like, bend and twirl, sweeping water molecules away, knocking the alcohol out of solution, reducing its solubility. So the reason that tert-butyl alcohol is soluble is it's more compact. So it's less hydrophobic. Hydrophobic is a term we use, phobic meaning fearing, less water fearing. So tert-butyl is less hydrophobic. Butanol, 1-butanol, is more hydrophobic, or water repelling. Okay, let's take a look at some nomenclature of alcohols and ethers. Now, we have already covered the nomenclature of alcohols in detail, but we have not looked at the nomenclature of alcohols in conjunction with ethers. So what we want to do right now is look at some molecules and see how we can name them. The first thing to note is that ethers are lower priority than alcohols. Okay, so ethers are lower priority than alcohols. And if we have both an ether and an alcohol that we have to name, we put the alcohol functional group in the root, and we bring the ether functional group up front as a prefix. So I find the longest carbon chain with the highest priority group on it. And so I number this way: 1, 2, 3, 4, 5. The longest carbon chain is 5 carbons with an alcohol at 2. This is a pentan-2-ol, pentanol. So we have a pentan-2-ol. Now the question is, how do you name the substituents? Well, the substituents are named very related to their alkyl substituents. That is, a CH3CH2 is an ethyl. A CH3 is a methyl, 3 carbons is a propyl. And the only difference is we're adding oxygen to the ethyl here. So if you add an oxygen, you take the YL ending of the alkyl group and replace it with oxy when it's a prefix. And so ethyl becomes ethoxy, and it's off the 5th carbon, so I have 5-ethoxy. All one word. 5-ethoxy pentan-2-ol. So when ethers are on molecules that also have alcohols, they are named as substituents. Give you another example. What would the substituent name have been if this had 2 methyls off of it? Well, what kind of alkyl is that? If you're careful, you would have known that this is an isobutyl group. Drop the YL because of the oxygen. Isobutyl becomes isobutoxy. And so in this case, we would have had a 5-isobutoxy. So you're now responsible for the nomenclature of substituent ethers when there's alcohols present. And then you'd have pentan-2-ol. So you can name very easily any substituents that have this ether functional group. But how do you name molecules that are simple ethers? What if you have, as we drew on the first case, just 2 alkyl groups attached to an oxygen? Well, then the highest priority group is the ether. And so ether is the root name. You name the alkyls attached to the oxygen. In this case, we have dimethyl ether. 2 words. If you have different alkyl groups, and I have an oxygen and say a methyl here, you typically pick the smallest substituent first, and you'd name this as methyl ethyl, and there's a space between each word, ether. So methyl ethyl ether means a methyl and an ethyl off of an oxygen. What do you do if you have two ether functional groups? In this case, IUPAC doesn't let you use the term diether. You must drop the ether terminology and name it like an alkane. This is an ethane. And you have two methoxy groups, so it becomes a 1,2-dimethoxy. So 1,2-dimethoxyethane. So when there's more than one ether, they are named as alkoxy groups. What about cyclic ethers, such as the three-membered ring system of epoxides? What about the epoxide? How are epoxides named? Well, the simple epoxide, which consists of an oxygen, a CH2, and a CH2, is referred to as ethylene oxide by common name, but the IUPAC name for this ring is Oxirane. When you have substituents off the ring, a unique difference about oxiranes is the numbering involved. For example, suppose I have a methyl and I have off the other side an ethyl. Now, in terms of nomenclature priority, methyl and ethyl have the same priority. And you might think you just number the carbons, but in actual fact, whenever you use the word oxirane, you must number the oxygen. Oxygen becomes number 1. Now you can go around either way, around either carbon. I'll go 2 this way, 3 that way. And so you see I've got a 2-ethyl, methyl oxirane. All one word. If, for example, I had with 2 methyls, an oxirane with 2 methyls off of one side, like this, that would be a 2,2-dimethyl oxirane. So there you have it, a quick run through of some of the nomenclature that we see in ethers and epoxides in conjunction with alcohol nomenclature. Well, let us begin looking at the chemistry, and we're going to start by looking at alcohols first, then move into ethers and epoxides a little later on. In the alcohol area, what we're interested in examining first is the preparation of alcohols. Now, we've already seen some reactions for the preparation of alcohols, and we're going to review them here again and look at some of them. For example, reactions with alkyl halides. We learned that primary alkyl halides such as propylbromide will readily react with hydroxide or even water under proper conditions to provide us with an alcohol. Now, you'll notice there's a triangle for heat in your notes when you look at this reaction. Because it's primary, the alkyl halide can be heated quite a bit without the threat of elimination predominating. And so you can actually raise the temperature a bit. However, I have said in this course the triangle will actually represent raising the heat high enough to favor elimination. So let's remove that triangle. Suffice to know that you can go to hundreds of degrees. You have to go to hundreds of degrees to get elimination to actually begin to predominate in this case. So we have examined substitution nucleophilic bimolecular. This is SN2. Primaries go SN2. We could use a tertiary, keep the temperature low, like tert-butyl bromide, with water, weak base, and allow the SN1 to occur, and make tert-butyl alcohol. So the first reaction that we have learned in our preparation of alcohols are the substitution reactions. SN2 and SN1. So we can look at those as a methodology for preparing alcohols. We have also examined previously the use of Grignard reagents. Just last Scribblecast, we discussed Grignard reagents, and the products of many of those reactions were alcohols. For example, if we took, I'm using GR for Grignard reagent. If we took a Grignard reagent plus methanal, we generated a primary alcohol. I suggest you turn back to that reaction. In fact, let's draw it out. It's not that hard. So we had methanal and let's add ethyl magnesium bromide. As our Grignard. 2H3O plus. What's the 1 and a 2 mean? 1 and 2 mean two separate steps. The delta minus on the Grignard is attracted to delta plus on the carbon. So the ethyl adds here, then the acid protonates the oxygen. Very nice reaction and yields a primary alcohol. A new Grignard reaction is the reaction of Grignard with Oxirane. Grignard plus Oxirane will also give us a primary alcohol. But it gives us a primary alcohol with 2 carbons more than the Grignard. The Grignard plus methanal only gave us 1 carbon more than the Grignard. So this would have been the carbon from the aldehyde. Here are the carbons from the Grignard. Grignard, which is ethyl magnesium bromide, so methanal gave us one carbon more. How does the Oxirane reaction work? Well, here's Oxirane. Suppose I hit this with, I don't know, let's use propyl magnesium bromide. And then 2H3 plus. Well, the propyl magnesium bromide, as usual, has a delta minus on carbon, delta plus on magnesium. Delta plus, delta minus. In the Oxirane, there's a delta minus on oxygen, so there's delta pluses on the carbon. And the delta minus of a Grignard is going to be attracted to one of those carbons. When you form a bond between this ethyl and the CH2, that's 5 bonds, so one bond's got a rupture, and what happens is the ring bond pops open, so you get the electrons moving towards the oxygen. The net result of this, of course, will look something like this. So you see the propyl group that came from the Grignard. You see the 2 carbons from the Oxirane. And so what you see is that effectively we're adding 2 carbons to the Grignard, and the O- is ready to be protonated when you throw in the H3O+. So effectively, you've made a primary alcohol where you've added 2 carbons to the Grignard reagent. So there's the propyl from the Grignard. And now the 2 CH2s from the Oxirane. There's the alcohol. So this came from the Oxirane, and this came from the Grignard. That came from the Oxirane. Remember reaction with ethanal? We did this, and I suggest you go back and look at it. All other aldehydes, other than methanal, produce secondary. They produce secondary alcohols. So if you hit this with methyl magnesium bromide, say, followed by H3O+, then what you end up with is the secondary alcohol, isopropyl alcohol, or 2-propanol. All other aldehydes give you secondary alcohols. What's interesting is you can get a fairly more complicated procedure happening with an ester that will also produce a secondary alcohol. Why not look at this ester? methyl methanoate. What happens if we hit this with the same reagent? Let's write that out again and give ourselves as much room as we can. So methyl methanoate, and I'm going to hit this with 1 methyl magnesium bromide dissolved in ether, let that react, and then 2 add H3O+. Well, what happens? Let's consider the first step. What happens when you throw in the methyl magnesium bromide? Well, again, as usual, magnesium delta's plus. There's a delta minus here on the methyl. The delta minus is attracted to the delta plus of the carbon, 2 electronegative oxygens there. So what's going to happen is the methyl carbon is going to attack, right? So I'm going to take those pluses and minuses away. The carbon's going to attack there, and the pi bond will move out to the oxygen. And we'll get something that looks like this. Now this species is an intermediate, and it's fairly short-lived. What happens next is a bit unusual and begs some explanation. Typically, we refer to the removal of OCH3- as an unfavorable one. We would refer to OCH3- as a powerful base. Methoxide is a powerful base, and hence a bad leaving group. And yet, what I'm going to do is I'm going to bring a lone pair back in to reform the pi bond and kick out OCH3-. And so what we have to do is essentially explain why that happens. So I've made a pi bond here. I'm going to move this methyl up to the side. So this is the methyl that came from my Grignard. And what got kicked out is the methyl O-. Now you may recall in lecture that I spent some time talking about what is meant when you say something is a strong or weak base. I said occasionally you find in lectures I'm referring to something as a strong base or strong nucleophile. And then a little later on I may be referring to it as a weak base or nucleophile. The terms strong and weak are relative terms. They depend on what you're comparing it to. Typically methoxide, because it's a fairly strong base, is a poor leaving group. Well, what do I mean by poor leaving group? I mean it doesn't readily leave. But that doesn't mean it's impossible to kick out. It really depends on what you're forming. Methoxide will act as a leaving group in cases where you're reforming a C double bond O. The C double bond O functional group, the carbonyl group, is relatively strong, and you do get quite a bit of energy back from its formation. It's energy sufficient to allow for the methoxide to act as a leaving group in this case. What's interesting, however, is you can't stop this reaction at the aldehyde. Your yields of aldehyde typically are not great. You see, the aldehyde itself is also subject to attack by Grignard. And because of that, plus the fact that there are better ways to make aldehyde, this reaction path is typically not used to make this molecule. So often, to ensure that we drive the reaction to completion, we will attack it with a second equivalent of methyl magnesium bromide. Now once again, when we throw in this methyl magnesium bromide, and by the way, methyl magnesium bromide, even if you didn't have two equivalents, would be starting to attack the aldehyde. The delta plus on the magnesium, delta minus on the carbon. That delta minus is attracted to the delta plus on the carbon. The delta plus on the carbon, so this methyl minus comes in and attacks here, and the pi bond moves out again. Okay, are we going to reform the carbonyl? Is there anything we can kick off? Methoxide was a pretty powerful base. It's still left. Well, now you see we've put a methyl group on. We've added another methyl. If we were to reform the pi bond and kick something out, we'd have to kick out either CH3 minus or H minus. And CH3 minus and H minus are far more powerful bases than CH3O minus. Methoxide minus is a far weaker base than methyl minus or H minus. So bringing the pi lone pair back in to create a pi and kicking one of these things out is too high energy and just doesn't happen. So what happens next is our H3O plus is added to solution. We protonate, and you see what's going to happen. You see what's going to happen. We're going to have a methyl, a CH, a methyl, an OH. And methanoates produce secondary alcohols. And here we produce isopropyl alcohol. This is the only ester that produces secondary alcohols. There must be an H here. If there is an H there off of the ester, it is a methanoate. You can have different groups here. You could have ethyl, methyl off the oxygen, but you must have an H there, and it's a methanoate. Then you will produce a secondary alcohol. Well, last Scribblecast lecture, we looked at the reaction of ketones, Grignard reagent plus ketone gave us tertiary alcohol. And just to refresh your memory, I'll give you the example you were given. I believe we used Benzophenone in that case as the ketone. So we had aromatic rings. I'll put dots for my carbons so they're visible. And so there's Benzophenone, and we hit it with, I believe, methyl magnesium bromide. And you could use methyl magnesium chloride. You could have made it from methyl chloride. It doesn't matter. I'll use methyl magnesium chloride this time. And 2 H3O plus. Again, the 1 and the 2 means two separate steps. Let the methyl magnesium chloride react completely, then react it with acid. And what you got here was an alcohol. And indeed, it's tertiary. It had the 2 phenyl groups still on the ring. And your methyl. So it gave us a tertiary alcohol. If I was to name this longest carbon chain with highest priority group, 1,2, it's an ethanol. This would be a 1,1-diphenyl ethanol. Okay, so we have an OH. Remember that benzyl alcohol is a common name. We have OH off a tertiary carbon here. The methyl minus was attracted delta plus in the carbonyl. And you get tertiary alcohols. Well, it turns out that Grignard, reacting with any other ester other than methanoate, any other ester, will generate a tertiary alcohol. And actually this is the reaction conducted in one of your organic chemistry lab experiments. And so I might as well utilize as an example, although it differs from what you're given in the handout notes. Let's try the example from the lab, the preparation of triphenyl carbonyl from methyl benzoate. So let's look at our ester. Our ester is the molecule methyl benzoate. And we're going to react this with phenyl magnesium bromide in ether, and then add acid. Okay, we're going to react this, as I said, with phenyl magnesium bromide, and the phenyl group is attracted to the carbonyl. Because as usual, Mg is delta plus, so there's a delta minus on this carbon. Delta minus on the carbon attached to magnesium. And the oxygen's a delta minus, so there's a delta plus on that carbon. That means he's going to attack here. The pi electrons will move out on the oxygen. This is a short-lived intermediate, and as usual, as we did in the previous case, the pi lone pair comes back in to create pi electrons. 2 electrons go out on the oxygen, and we recreate. We kick out methoxide, CH3O-, and we make an intermediate species, a stable molecule that is an intermediate, called diphenylketone in common nomenclature. What is the IUPAC name of this guy? Well, it was the reagent from last reaction. It's benzophenone. Now, just like the methanoate case in making aldehydes, these esters do not provide a good way to make ketones. It's very difficult to get any substantial yield of the ketone. You see, the ketone is also got delta plus on the carbonyl, and hence is subjected to attack by Grignard. So it is very difficult to stop the reaction, make the reaction only attack the ester and not the ketone. And so yields of ketone are very low, and since there's better ways of making ketone, this is typically not the way. And when you do this reaction, you typically throw enough phenyl magnesium bromide in to drive it all the way. And so we continue our reaction. We hit it, we hit it once again with phenyl magnesium bromide. Whether we use 2 equivalents or 1, this will happen. And since it does happen, you might as well throw in 2 equivalents and make sure it goes all the way. Phenyl magnesium bromide will go in, attack the carbonyl. Lone pair of electrons will move out on the oxygen. Now, will we reform a carbonyl now? Well, if we were to try to rebuild a C double bond O, we'd have to kick out a phenyl minus. Phenyl minus is carbon minus and extremely basic. That negative charge is not delocalized in the ring. It's only stuck on a carbon. Because it's so basic, it's a terrible leaving group. Far worse than methoxide. So it does not reform the carbonyl. Nothing is kicked out. And what happens is we add acid, and the acid protonates the O-. And so we end up with OH, C, with 3 phenyl groups off of it. And I'll put dots here so you can see the 6 carbons clearly. So my 6 carbons. And 3 aromatic rings. This molecule is called triphenylcarbonyl. That's its current common name. IUPAC would be triphenylmethanol. So there you have it. All other esters other than methanoate, here we have methyl benzoate, generate tertiary alcohols. Tertiary alcohols. Another methodology for the production of alcohols is the reaction of the carbonyl aldehydes or ketones with reducing agents. In other words, we carry out reduction of carbonyl compounds. Now, it turns out with proper reducing agents, both aldehydes and ketones and I usually use, it's very common in textbook, H in square brackets. That just simply means reducing agent. With the proper reducing agent, aldehydes will be reduced to primary alcohols and ketones will be reduced to secondary alcohols. Again, remember R stands for alkyl groups. Now there are 2 suitable reducing agents. One type of reducing agent is where you take H2 gas, which by itself would do nothing because it's too stable, and you add a metal catalyst. In this case, we're going to use nickel. Nickel acts as a catalyst to activate hydrogen. We'll talk more about this catalytic hydrogenation reaction when we look at it again in alkene chemistry. This is often accompanied by heat and pressure. So sometimes you have to put the H2 gas under some pressure. The second reducing agent that may be used is a 2-step process. Well, first you use a metal hydride. The metal hydride we typically use is sodium borohydride, BH4. BH4 is negatively charged. So you have sodium plus BH4 minus. Boron is less electronegative than hydrogen. So BH4 is a source of H minus. Effectively, it's like doing what we did with the Grignard, where we had methyl minus act as a nucleophile. Here we have H minus act as a nucleophile. And the H minus attacks the carbonyl. The second step, like in Grignard's, is the addition of H3O plus to destroy any excess boron salts, and also to protonate the alcohol that forms. The reducing agent itself is the metal hydride, though. Okay, so with these two reagents, it is possible to reduce carbonyl compounds and prepare alcohols. Let's look at both reactions more closely with some examples. Here is a molecule that we know as an aldehyde, benzaldehyde. If we hit benzaldehyde with H2 gas, and we use nickel as our catalyst, we put in some heat, and we put in some pressure, and you may find the heat and pressure omitted because in some reactions you don't need much heat, no more than room temperature, and sometimes the pressure you don't need, it just goes a little slower. So you can put just H2 gas and nickel over the arrow, but it's equally appropriate just to put heat and pressure there as well. So it really, the heat and pressure is optional, but you often find it written. What happens is it adds an H to the carbon and an H to the oxygen. And so you get CH2OH, or benzyl alcohol, phenylmethanol. Okay? Let's do one with the other reagent. Now let's use our friend a ketone. We've used them several times now, benzophenone. I can use benzophenone with sodium borohydride. Sodium borohydride is a source of H-. H- will act as a nucleophile and attack the carbon. So if you like, the sodium borohydride BH4 puts an H on the carbon. So this H on carbon came from the BH4. That leaves BH3. Now if you remember 6 electrons around boron, boron has an empty orbital. So quite often the BH3 will interact or actually bond to the oxygen. So the BH3 bonds to the oxygen, and because of the empty orbital in boron, you get a covalent bond to boron. Now you can leave that out and omit it. It's understood that it's there, and in fact it's interesting to note that the BH3 also has electronegative H- off of the boron, which can further react. Now, the next step, we have H3O+, we add it, and what the H3O+ does is protonate the oxygen, the O-. And the BH3 is destroyed and becomes soluble boron salts in the water layer. And so, when we're done and the acid protonates the resultant alcohol, we have our 2 phenols, we have H, and we have OH. Excellent. And so you can see how ketones can produce a secondary alcohol, and aldehydes produce the primary alcohol. Now let me just say, you could have switched the reagents. You could have used sodium borohydride and acid in the top reaction, and in this bottom reaction you could have used H2 gas, nickel, heat, and pressure. And once again, let's emphasize that the heat and pressure is a possibility, optional, because heat can mean room temperature, pressure can mean atmospheric pressure. The reaction just goes slightly more slowly. Often, though, you pressure it up just to make the reaction go faster and hopefully increase your yields. Next reaction that we're going to actually just introduce here, not talk much about, is a method for creating alcohols from alkenes. And we're going to look at this again when we look at alkene chemistry. So we're not going to talk a lot about how it happens. It is just an example preparation of an alcohol that you'll have to remember. If we take H2O in acid, okay, you could write H3O plus or H plus here. What happens is you add an H to one carbon and an OH to the other carbon, and you produce an alcohol. So essentially across the pi bond, water and acid will add an H2O. It looks like it just adds H2O. It splits up the H2O molecule. It looks like the OH of the H2O goes on one carbon and the other H goes on the other carbon. And you can think of it that way for now if you like. So we have water effectively adding across the double bond when water is an acid, and we produce, in this case, a secondary alcohol. This is referred to as a hydration reaction because you're adding water to the molecule. And so it's the hydration of alkenes. Hydration of alkenes produces an alcohol.